Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Alright, so for this problem, I think the hardest part is just trying to understand the directions that we have. So a typical compass, just for starters, has north up top, south, east on the right, and west on the left. So we're told we have the Earth with a magnetic field, the Earth's magnetic field B, and it's at an angle that is below the horizontal. So what I'm going to do to represent that is turn this compass flat, with west pointing back into the page, east coming out of the page, and north heading to the right, like so. So we have north. Let's do it in black. Actually, yeah, let's do it in red. So we have north pointing to the right, which, let's put a point here to signify our origin, which means south is this way. This is north, south. So west is going back into the page. And east is coming out of the page. Now I'm doing this because this is a three-dimensional problem they're having us do. So I'm going to draw it with the three-dimensional axis. So here's the compass laid flat. Now we have two other dimensions, which is up and down. So this makes a 3D graph. So up and down. Now we have our magnetic field is below the horizontal. So in the perspective of the Earth, that would be going down into the ground. If you look north, that would be angled down towards the ground. And this is at theta 1, at angle theta 1, which I'm just going to call theta 1 here. And now we have a bullet that's fired up above the horizontal at an angle of theta 2. Now these are in this up north plane, the plane created between the up axis and the north axis. So this W axis is going back into the page. So this would come down here and touch north, and this would come down and touch, or this would come up and touch north. So those are our angles that we have. So the bullet is fired upwards towards the sky, the magnetic field is angled downwards into the ground, both pointing north, or northward. So we have the magnetic field of the Earth, we have the velocity the bullet is fired at, we have the force on the bullet, and we need to find out what our overall angle is. I'm going to call it theta t for the total angle. Because we want to use the equation for force with the electric field, or magnetic field. So our equation for that, because we want to find what the charge of the bullet is, we're told the bullet has a charge on it. Now, remember, this is for the magnitude, this charge in this equation. So we'll have to find our charge of the bullet another way. So this is the charge times the velocity times the magnetic field sine of theta. And in this case, this is going to be theta t. It's the total angle, which in this case is the angle between the magnetic field and the velocity, traveling the direction of the velocity, which is just angle 1 plus angle 2. So theta t is equal to the sum of theta 1 and theta 2. So that's our total angle. It's the angle between both of these two here. So we have one below the horizontal and one above it, so it's the sum of those two angles. Now we can use our right-hand rule to find the direction that we would get. Your thumb, so our velocity is directed upward. It has an upward component, upward and to the north, but it would be up in this case for your right-hand rule. And our magnetic field is down. So you want to point your hand down, and your thumb, or no, you want to point your fingers north, and your thumb should be pointing up. And then your palm faces in the direction that the force should be in, or the force. So we have our angle between velocity and magnetic field. So your fingers point down in the magnetic field direction. Your thumb points along the velocity, which in this case is directed up. And then your palm should point in the direction the force is in. So in our case, we have it pointing backwards into the page, into the west direction. But we're told that the net force points east, which means that our right-hand rule doesn't work. It's the opposite of our right-hand rule, which we know means that our charge is negative. So we have a negative value of Q. So we'll have to remember to keep that negative when we find our charge. And that's because, once again, it's the opposite of what the right-hand rule tells you. Due to the right-hand rule, it should be facing in the westward direction, but we're told that it goes east, which means that it's negative. So now we can plug in all these numbers and find our Q, and we'll know the direction. So we have everything we need now. We just have to solve for Q, which is simply rearranging this equation. Solving for Q. Velocity times the magnetic field, and we need that sine of theta. Let's make that be a little better. And this is sine of theta t, the total angle. Oops. Theta t. And this will give you the magnitude. So you get the direction from your right-hand rule, or you get the sign of the charge from the right-hand rule, and you get the magnitude of Q. This is just the magnitude. So we know it has to be negative. Minus Q. And there you have it.